Hello. In this video, we're going to talk about the addition rule for probability. We're going to be calculating the probabilities of more complicated events formed by combining separate events. And one of the ways that we combine events to form more complicated events is through this magical word OR. If we're interested in calculating the probability that A occurs or event B occurs, or potentially both, this type of OR is an inclusive OR, meaning A or B or both. It's not an exclusive OR, like when you cheat on your girlfriend and then your girlfriend gives you an ultimatum and says it's either her or me. This is the type of her or me or both. So if I'm interested in calculating the probability that A occurs or B occurs, or potentially both, then I'm just going to add the probability that A occurs with the probability that B occurs. With one major caveat though. We need to be careful about those outcomes that are shared between events A and B. We only want to count them once. Now, a lot of times when people apply the addition rule to calculate probabilities, they have no problems with the addition because that's what you remember. It's intuitive that way. If I want to find the probability of A or B, you hear that magical word OR and it rings to your mind, I need to be adding probabilities. But you also need to remember about the potential of counting outcomes twice. Let me give you an example of this now. Here's an exercise from your textbook. And what you're given here is sort of like a frequency table. Here we have a bunch of classes representing the ages of people approached to fill out a survey, and we have their corresponding frequencies, but they're broken up further or contingent on measurements of some other qualities about the people we approached. For example, for all the people between the ages of 18 to 21 that we approached to fill out this survey, 73 responded and 11 refused. For all those people between the ages of 22 to 29, 255 responded and 20 did not. So this is what we call a contingency distribution or a contingency table. And one of the things that you'll be interested in doing with a contingency table is calculating the marginal distribution. For example, what we're going to do here is to add up all the columns to find column totals and to add up the rows to find the row totals, to find the marginal distributions or the marginal totals of this table. So if I were to start adding up all the 18 to 21-year-olds, the first column, I get 84. The total number of 22 to 29-year-olds is 275. The total number of 30 to 39-year-olds is 278. The total number of 40 to 49-year-olds is 152. The total number of 50 to 59-year-olds is 165. And finally, the total number of 60 and over is 251. And this gives me the total numbers per age group. Now, let's also find the total of the first and second column. The total number of people who responded, which is going to be the total of the first row of responses, is 1,049. And the total number of people who refused is going to be 156. And now, if we counted our totals, the column totals and row totals correctly, we better get the size of our sample, which is 1,205. Now, given this bit of information, we now know the total number or the frequency, total frequency of our contingency table or of our sample. Now, if someone were to ask us to calculate the relative frequency probability or empirical probability that a selected person was 18 to 21 years old or 50 to 59 years old, we recognize that this is in fact the probability of the event that the person was 18 to 21 years old or the event that the person was 50 to 59 years old. So if I want to calculate this probability, it truly is as simple as it seems. To find the probability of the event that the selected person was 18 to 21 years old or 50 to 59 years old, right? This is another event, right? We select a person at random and we're interested in the likelihood that that selected person was between 18 to 21 or 50 to 59. You think in your mind, well, this is an or probability. I'm just going to add up the corresponding probabilities. The probability that someone is between the ages of 18 to 21, well, there were 84 of those people out of 1,205 total. And the probability of the event that someone's between the ages of 50 to 59 is going to be calculated by taking the total number of people who are between the ages of 50 to 59, 165, and dividing that by the size of your sample. And then, to finish this off, the probability that a randomly selected person was between the ages of 18 to 21 or 50 to 59. It's just going to be the sum of those probabilities. Now, and it really is just as simple as that. We break out our calculators, add up 84 plus 165, and we find out that the probability is going to be 249 over 1,205. Which makes sense because if we want to know how many people are 18 to 21 or 50 to 59, that's 249, right? 84 of the 18 to 21-year-olds, 165 of the 50 to 59-year-olds. And there's no possibility that a randomly selected person is, at the same time, both 18 to 21 and at the same time 50 to 59. Now, let's look at this from a different perspective, because in this case, both of our events can't happen at the same time. You can't be both 18 to 21 or 50 to 59. You have to be one or the other. These two events are what we call disjoint because they have no people or outcomes in common. But now, consider this exercise. What is the probability now that a selected person refused to respond or is over 59 years old? Now, here we're like, all right, we're going to calculate the probability. This is an or probability, so you think we're going to add some stuff. So I want to know what's the probability now of the event someone refused or is over 59 years old. And this is the event that someone's over 59. Now, to calculate this probability, you should notice something. The number of people who refused, when we calculated now the marginal distribution, was 156. And the number of people who were over 59, that is to say, the number of people who are 60 and over, was 251. Out of a total of 1,205 people. So if I want to calculate the probability of the event that a randomly selected person refused to participate, that's going to be 156 out of 1,205 people. And if I'm interested in the probability now that a randomly selected person is over the age of 59, that is to say 60 and over, that's going to be 251 out of 1,205. But now, this is where you have to be careful because since this is an OR probability, you correctly add those two probabilities up. But look what happened when you do that. By adding up all the outcomes that resulted in a refusal, you get a total of 156. That is to say, 11 plus 20 plus 33 plus 16 plus 27 plus 49 is equal to 156, out of 1,205. Now, if you add up all the people who are over 59, this column, that's 202 and 49 to give you a total of 251 out of 1,205. But now the problem is revealed. In both of those totals now, you've counted these 49 people who are both 60 and over and refuse to participate in the study. You've counted these 49 people twice. So as a consequence, we subtract one of those groups of 49. 49, and this out of 1,205. Plugging this into our calculator, 156 plus 251 minus 49 gives me 358 out of 1,205. Now, if you're just cognizant about the fact not to duplicate the 49, you approach one of these probabilities and you're like, I want the people who refused or the people who are over 60 and over, and you just count all of these values, making sure that you don't count the 49 twice, that's fine. Then there's no special formula to remember. But there are often at times where your probabilities are not going to be presented this way, so you'll have to be making sure that you subtract the appropriate probability. Let's go back to the formula and observe how we've applied that. The probability that someone refused or is 60 and over is the probability that someone refused plus the probability that someone's 60 or over minus the numbers we counted twice, which is to say we subtract really the probability that we counted twice. I skipped over a slide, and that's because what I've just described, by making sure that you only count those outcomes they share in common once, is what we call the intuitive addition rule, which is, we want to make sure that we calculate the probability in such a way that every outcome between A and B is only counted once. And that's the addition rule for probability.